Good afternoon, teacher and student. Welcome to attend this talk, Computer That Learn from Experience, Deep Learning and its Application. I'm Susanna. I will be the MC for today's program. First of all, may I invite our honorable speaker, Dr. Chen, to introduce machine learning to us. Dr. Chen, please.
We're both very excited to give a talk now. Hope that we can show you what people are doing with machine learning and also what are the challenges with it. So it's a great technology, but it also has some weaknesses that we need to fix. So there's a lot of challenges, also a lot of opportunities, which means it's a good thing to look at. Okay. So first of all, where do we see machine learning in our daily lives? Okay, so if you just go to Google, basically their entire company is based on machine learning. Right? Their goal is to organize information in the world. Information is data, and machine learning models need data to learn about the world. Okay, so if you use OK Google, right, the speech recognition software, it's based on machine learning. They have people say phrases to the computer, and the computer learns how to recognize those phrases. If you use Google Street View, they use machine learning to detect where people's faces are. Okay? And this becomes a privacy issue in Street View, so they remove the face or they blur out the face so people can't identify you. Right? But they also use machine learning to detect characters, like numbers, street signs in Street View. And why do they need to do that? So they know precisely where the building is. When you search for a particular building, they know exactly where it is and they can point you to it. And also, if you use autocomplete, so if you type a partial phrase and it will fill in the rest of it for you, this is all based on machine learning. It basically learns, the computer will learn all the different types of phrases that people could type from that set of strings, set of characters. Okay? And then given the context, like maybe previously you were searching for something, and given the context, it will fill in something relevant for you. Right? This is all done through machine learning. Okay. When you use your phone and you take a picture, it draws a box around the face. Right? That's basically done using a face detection algorithm that's trained from a lot of faces. Okay? And then it can also recognize your face, like in Facebook. Okay? Those are kind of the online applications. There's also a lot of applications in business. So in finance, people use this to detect credit card fraud. Okay? So if you buy something, so this happened to me once. So I was in the US at an outlet store, and I was with my brother-in-law, and he asked me to buy 5 Coach purses, which is something that I don't normally buy. Okay, and the credit card didn't go through the first time. Credit card didn't go through the second time. So I switched to another credit card. And then 5 minutes later, I got a phone call from the bank and said, did you just try to buy 5 Coach bags? I was like, yes, I did. He's like, okay, yeah, we just flagged it because you don't normally do that. Right, so that's all done with machine learning. You can also do stock trading, so portfolio optimization. Okay. In retail, they use it for recommendation systems. Right? So if I buy something from Amazon.com, right, it will recommend me other things that I might want to buy that other people have purchased. Okay? And the same thing for Netflix. If I like a movie, then it will see what other people have liked and try to recommend these for me. Okay. And finally, people use it in games. So if you play Connect, the way that it detects the human pose is using a special camera, and that special camera uses machine learning to detect all the joints and positions of the person. Okay, and then also in self-driving cars, so basically all the sensing and all the movement is determined through machine learning. They teach the car how to see people, where they are, how they behave, okay? And then they also teach the car how to react to those when they want to navigate or avoid obstacles. Okay. So that's the motivation, and I hope that you may not know that it's doing these in the background, but it is, okay? And it's only going to be more prevalent in our lives. Okay, so let's talk about what exactly is machine learning. Okay, so this is a phrase coined a long time ago by Arthur Sandel. Okay, and machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. Okay, and the example is if I want to make a program for a computer to play checkers, right? I could think of all the rules of playing checkers and all my strategies, right? And maybe when I would do this and when I would do that. Okay? But it's much easier just to create a program where the computer can play itself. Right? And as it's playing itself, it discovers what strategies are good or what strategies are bad. Right? And from this, it can learn from its own experience. Okay? Another example is if we want to do handwritten digit recognition. So these are some numbers in an image. Okay? And I want to write a program to detect all of these numbers, to identify the numbers. Okay? So if you think about it, okay, an image is just like in this case, it's a 28 by 28 pixel image. Okay? And that's 784 numbers, okay, in the computer. And there's a lot of different variations about how a number can appear. For example, the 0, okay, you would think that a 0 is a complete circle, but some people are funny, they'll write it a little bit slanted. Some people use a thicker marker, some people use a thinner marker. Some people are in a hurry and they won't complete the 0. Right? So there's a lot of these different rules that you need to think about if you wanted to write this program. Okay? And the machine learning solution is basically just collect a lot of data, and instead of writing a program on how to detect the numbers, you write a program to teach the computer how to learn them. Okay? So instead of writing the program, we're writing to write the program. Okay, so we can go a little bit further in this. So in 1997, Tom Mitchell described this well-posed learning problem. Okay, and I like this definition because it gives you everything that's important about how machine learning works. Okay. So he said that a computer program is said to learn from experience E with respect to some class of task T and performance measure P if its performance at task in T as measured by P improves with experience E. Okay. So that's a very kind of rigorous statement for saying something very simple, which is the computer gets better at recognizing the digits as it sees more examples. Okay. And it gets better according to some measurement that we objectively measure, some objective measurement. In this case, maybe how often it makes a mistake. Okay. So we can take a closer look. So first of all, we have a class of tasks T. Okay. So that means that machine learning is task specific. Right? We want to teach a computer to do a certain thing, like recognize digits, recognize faces, recognize dogs. Okay? We're not interested in general AI. General AI with reasoning and all this stuff is not in the purview of machine learning. Okay? The second thing is we have a performance measure P. Okay? And in some cases, this could be the error that the algorithm makes. Okay? And our goal is to minimize or to reduce this error. Okay, so that means that in the end, we have something called the loss function, which measures how good this model is. And our goal for learning the model is to reduce this loss function. Okay, so that means that we frame learning as an optimization problem, as a problem of how to reduce a value. Okay. And the final thing that is important here is the experience E. Okay? Experience just means data, right? And more data is always better. So this is a complete data-driven method. So here are a few topics in machine learning. So basically the 5 main areas: supervised learning, unsupervised learning, reinforcement learning, learning theory, and deep learning. And I'll go through these very quickly, very briefly, and then we'll talk about it in more detail, just to get you an overview. Okay. So supervised learning means that our data that we have has both an input and an output. That means we have an image, right? And we also have an output. The image is the input, and our output is our prediction. So we want to say whether this digit is a 3 or an 8. Okay. Okay. And that's our goal is to learn a function that maps from this input to a specific output. Okay. And an example here is for classification. So each one of these little dots represents one of the images, and then our goal is to draw this line here to separate the space so we can predict if I get a new dot here, whether it should be a 3 or an 8 or a new image. Okay. Another example is called regression. That just means that our output values are real numbers instead of classes. And in this case, we want to learn this function in order to make a prediction about, in this example, given the number of doctors per million, what is the life expectancy? Okay. So this is called a regression problem. Okay. A second type of learning is called unsupervised learning. Okay. That means that we only have the inputs. So we only have images, or we only have documents. Okay, and now our goal is to organize them somehow. Okay, so 2 ways of doing this. One is called clustering, which means that we try to find similar examples and put them together. Okay, so for example, when you search on the web, right, if you use Google image search, right, you'll see a little bar after you click on an image that says similar images to this one. Right? So that's a clustering problem. They have an image, and now they want to find similar items. Okay. Another part of this is for visualization. So we can take something that is potentially hard to organize, and we can put it into a nice projection or a nice image, a two-dimensional or three-dimensional representation, and we can see how things are similar to each other. Okay. The third type of learning is called reinforcement learning, okay, and this is a little bit different from the other ones. So the idea of reinforcement learning is that we have an agent in an environment, okay, and the goal of the agent is to make some actions, okay, and try to get better, or to get a reward. Okay, so an example is that we have a mouse robot inside a maze, okay, and the mouse can see where it is, okay, and it can also perform an action like go straight, turn left, or turn right, or stay where they are. Okay, and the mouse makes some actions in the maze, okay, and eventually the mouse gets a reward, finds the cheese, okay, and then it has to remember what were the actions that gave me this reward. Okay, so it's a little bit different, and this reinforcement learning is actually used to create game agents. So if you've heard of AlphaGo, which is Google's reinforcement learning program for playing Go, it's based on this idea of reinforcement learning. Okay, so the fourth topic is on learning theory. Okay, and this is more about, it's not about the application of machine learning to do a particular task. It's talking about why does machine learning work. Okay, so we can do all of these things. We can create a loss function, we can program the computer, we can minimize the loss function, we can get a detector or a classifier. Okay? But then we ought to know mathematically why does this work, and will it always work? Okay, so that's the idea about machine learning. It's really about learning theory. It's more about the mathematics behind why it should work. Okay, and finally, the final topic is deep learning. Okay, and this is something that appeared recently in the past maybe 10 years. Okay, deep learning is machine learning using these neural networks, multi-layer neural networks. Okay, and here deep means that we use more layers in the network. Okay, and the reason why this became more popular recently, so neural networks were invented like in the 50s and 60s and 70s. Okay, and the reason why it's more popular now is because of three things. So one is that we have more data. So because of the internet, now we can collect a lot of images, and we can label those images by just asking people, who is this person? And on Facebook, you would love to do this because you get to see your friend. But Facebook sees this as you're giving us data. You're labeling the data for us for free, actually. Okay. We have faster processors. So in particular, we have these GPUs, or graphics cards. Okay, and actually, graphics card is just a very fast linear algebra machine. It does a lot of calculations very quickly in order to project your triangles onto the screen to make your little game character. Okay? And then actually, we can use that in deep learning to accelerate the computation. Okay? And the final thing is that we have improved algorithms and improved ways to learn these neural networks when they're deep. Okay? And we'll talk about this a little bit more. Okay? So this is the introduction, and to give you kind of an overview, and now we'll talk more about the actual details about machine learning and deep learning. So I'll give a brief introduction to machine learning, and then we'll show how it relates to deep learning. And then I'll talk about some case studies about different types of architectures that people have developed to solve particular tasks. Okay. So first of all, let's just start with a simple supervised learning problem. So suppose we want to predict a person's weight from their height. Okay? And we decide to use machine learning for this. So we collect some data of people's height and weight here. So x-axis is the height, y-axis is the weight, and these are the points that we've collected. Okay, and now we need to learn some kind of function for this. So let's assume that the relationship between height and weight is a line. Okay, so in your algebra class, I hope that you're familiar with this equation. So the y is equal to ax plus b, or mx plus b. So a is the slope of the line, and b is the y-intercept. Okay, and we just say this is a function of x. Okay, so how do we fit a line to this data? Well, if I had 2 points, right, this would be very easy. Right? You just say 2 points to find a line, and I could just draw a line directly through it. Right? But if I have more points, like in this case, and they all don't fall directly on a line, okay, then I have to think of something of how to do this. Okay, so it becomes a little bit more difficult. Okay. So we can't fit a line perfectly. Okay? So, and there will always be this error. So the line represents our predictions for each x, the prediction of y for each x. Okay? And if I look at the difference between one of the observations I have, the sample, and my prediction, then this is an error. This is called the prediction error. Okay? And I represent these with these little red lines. Okay? So what we can do is we can define something called a loss function, which is the measurement of how well this model works. Okay? We can define this loss function on the about the prediction errors. Okay? So for each point, we have x and a y value. Okay. And then in the prediction, I also have an x value and the predicted value, which is f of x. Okay. And then what we do is we just compute the difference between these two, so the length of this red line, okay, and then we square it. Okay. Why do we square it? Is because if we square it, then if we have a large error, it creates an even larger loss. So we want to penalize larger errors more than smaller errors, so that hopefully the line can fit with little error everywhere. Okay, and now you can, if we want to learn this, so there's many possible lines that we could choose. So here are 3 examples. Okay, so this line is a little bit tilted and has a little bit larger error than these 2. So many possible lines, this means there's many different settings of the line, the slope A and the intercept B. Okay, and each one of these settings of A and B will have a different loss that we can compute, or a different squared error. Okay. Then in the beginning, I said machine learning is an optimization problem. So in the end, we'll just say, okay, we have this loss. We can use this to select which one is the best model. Okay? So we pick the line that has the lowest total loss. Okay? Or in other words, we select the A and B so that it has the least loss, least total loss. Okay? And in this example, it's this one. So this one has loss 4.5, and I select this one. Okay? So that's the intuition. How do we actually do it? Okay. How do we find this minimum? So if I go back here, if you look at this, so A and B are the things we're trying to find, and then I square them. So this is roughly a quadratic equation. Right? It's a parabola like this. So our goal is basically to find the minimum of this quadratic equation. So in this case, we can do this through some algebra operations to find a solution, a closed form solution. Okay, so this is a nice example. Okay, and in machine learning, this is called linear regression, or least squares regression. Okay, now let's try to change the problem a little bit. Okay, now let's say we want to learn a classifier. Okay, we want to predict whether a person is an adult or a child based on their height, from their height. Okay, so again, we collect data of height, x, and now we also collect, instead of the weight, we collect a class. So in this case, the class is called y. Okay, and we'll say that y is 0 when it's a child, and y is 1 when it's adult. Okay, and here is the data that we collected. So the x-axis is the height, and the y-axis, there's only 2 possible values, 0 for child and 1 for adult. Okay, here there's maybe a short adult and a tall child. Okay, so again, we can try to use our same linear regression. So suppose we define this line, straight line again, okay, and we try to fit it to this data, we'll get something like this. Okay. So the problem here is that it doesn't really fit the data well, because the class can only have 2 values, 0 and 1. Okay. And here I'm predicting something weird. Like over here, I'm predicting like the class is 2. There's no class 2, it doesn't make sense. Okay. Here I'm predicting some negative number, it doesn't make sense. Okay, so how can we fix this? Okay, so the idea is that we take this line, okay, and we just squash it between 0 and 1. Okay. Mathematically, that means that we apply something called a sigmoid function, which looks like this. Okay, so now the function is squashed between 0 and 1. Okay, and in this region, right, the value is 0, and in this region, the value is 1. So this region is predicting class 0. This region is predicting class 1. Okay, in between, it has some value in between, mainly because there's people on opposite sides here. Okay, so roughly, the value here that we're predicting can be thought of this as a probability of it being a particular class. So this is a probability of it being class 1 or adult, given the height that we observe. Okay, so similar to regression, we'll also define a loss function to measure these prediction errors. Okay, so here is the possible sigmoid function. Okay, and then the difference between the orange line and the red dot is the prediction error. Okay, and in this case, we use something called a cross-entropy loss. Okay, so when the class is 1, then we say the loss is this minus log of the sigmoid. Okay, and this just means that we want to maximize the probability of class 1 from the function. That means we want to raise this orange line up to y equals 1. Okay, and from when y equals 0, then the loss is basically minus log of the probability of class 0. Okay, that means we want to maximize the probability for class 0. So we want to pull the orange line towards this red dot. Okay, so if we minimize the total loss of all the samples, then it will pull this orange line towards the dots on y equals 0, and the dots on y equals 1. Okay, and in this case, there happens to be 2 dots on the opposite side, so it can't do it perfectly. Okay, but it can kind of minimize the total probability error by setting the value of the line. Okay, so this is called logistic regression in machine learning or in statistics. Okay, and actually, this model is very popular in the past. So it was used before deep learning, so like in maybe 2000s. Google used logistic regression for everything. They just collected a lot of data, right, and then used it on everything. So it's a very powerful and simple model. Okay, okay, so we have this idea of minimizing the loss function, this cross-entropy loss. Okay, and the problem is that this cross-entropy loss is harder to optimize than the squared error loss that we use for linear regression. In particular, there's no solution that we can just write down in an equation form. Okay, so that means that we need to develop an optimization algorithm to optimize, to find the minimum value of this loss function. Okay. And the algorithm that we use here is called gradient descent. That means we iteratively reduce this loss function. Okay, and it works like this. So suppose we have our current solution here, and the value of the slope a. Okay, what we can do is we can compute the derivative of this function at this point. Okay, and what this derivative tells us is the derivative is basically the slope of the line that's tangent to the function. And the slope, the derivative tells us the slope at the point. The slope tells us which direction we can go to decrease this loss function. Okay, so in this case, right, if I move in this direction, then I'm increasing the loss function. If I move in this direction, then I will be decreasing the loss function. Okay, so that means that we know the direction that we can step. So we can step in this direction a little bit. Okay, and then that becomes our new solution. Okay, and hopefully we've reduced the loss function a little bit. Okay, and then I just repeat this until it converges or until I'm satisfied. Right, so I compute another derivative, I make another step, and I get another solution. Right, and I just repeat this until I get to a point that doesn't change. Okay, this is called gradient descent. Okay, so we use this to learn the logistic regression parameters. Okay, so this is in the example of the logistic regression I introduced only has one input, the height. Okay, but we can also extend it to have multiple inputs. Okay, and then in this figure, I show a representation of that. So the x-axis, the horizontal axis is the height, which I call x1. And the vertical axis is the weight of the person, called x2. Okay, and we want to predict whether the person is an adult or a child. Okay. And then for the logistic regression, what it will learn is a boundary, this straight line. Okay, and things on the right side of the boundary are considered as adults, class 1. And things on the left side of the boundary are considered as class 0 or child. Okay. And the function is just a combination of the different slope times the feature and then another slope times another. Okay. So the problem with this is that this function is with one input is a line. Okay. With two inputs, it's a plane, a surface, flat surface. Okay. And in general, it's always going to be a linear surface. Okay. So that means that we can't use this on more difficult problems or more complicated data where the boundary is not necessarily a straight line. Okay. So in this example, I can't find a straight line to be perfectly accurate, but I could find a curvy line that would work. Okay. So now the question is, how can I extend this to learn this curvy line? Okay. And that brings us to the idea of neural networks and deep learning. Okay. So now, how do we do that? Okay, so the idea is that we can use the same logistic regression unit, okay, and then we apply it to, instead of predicting the class, we just say we extract some feature. Okay. And once we've extracted these features, then we can try to use those new features as an input into a classifier. Okay, so here is the original data. Okay, and I want to extract some features, so I just learn a line, a logistic regression unit here, and things on the right of the line here are called class 1 or have value 1, and things on the left have feature value 0. Okay, I can do it again. Okay, now maybe I have a horizontal line, and things above the line have value 1, and things below the line have value 0. Okay. And now for each point, instead of representing it with x1 and x2, I represent it with z1 and z2. Okay, and what happens is the space will start to look like this. Okay, because I only have values of 0 and 1, so the points will start to be clustered towards the 0 and 1 regions of the space. For example, the points here, they have values where z1 is 1 and z2 is 1, and they are the points here. Okay, and the points over here, they have values that are close to z1 equals 0, and here z2 is equal to 0. So those points start to fall close to the origin. Okay, so now if I apply a classifier to this new space, okay, then actually I can do a good job. Okay, I can separate the class into child and adult. Okay, and then if I backtrack, right, you can actually show that this is equivalent to learning a non-straight line in the original space of x1, x2. Okay, so we can create a non-linear boundary for the data. Okay, and we basically do that by using this logistic regression unit successively. Okay. So each one of these units is called a neuron or a perceptron. Okay, and the idea actually came in trying to simulate a neuron in the human brain or in a brain in general. Okay, and the idea is like this. So in a normal brain, a physical brain or a biological brain, I guess. Okay, so the dendrites are here. They receive signals from other neurons, okay? And those are the inputs in our simulated neuron here. Okay? And what the neuron does is it collects these signals from the dendrites, okay? And if the signal is strong enough from the dendrites, if it's happy with it, then it will activate and it'll send a signal, another signal down the axon, okay? And this axon, it ends close to other dendrites of other neurons. Okay, so it's able to pass a message to the other neurons. Okay, and for the simulated neuron, it's the same. So we have inputs, which are from previous neurons, the previous features. We have an activation unit, which after it gets to a certain level, then it fires a signal, and that signal gets sent out to the next layer or to the next node. Okay, so there's a close, at least in the first order, it's similar to a brain. But a brain is much more complicated. There's actually other neurons that inhibit neurons and things like this. So we don't talk about that. But this is a first order approximation. Okay. Okay, so the neurons are organized into what we call layers. Okay, and each layer here extracts features from the neurons of the previous layers. Okay, and then the last layer is the logistic regression classifier that I talked about before. Okay, so this example, this is the input layer where I present, for example, an image. Then this is a hidden set of, called a hidden layer because we don't apply anything to it. Okay, and it takes, it's connected to the input layer. Okay, and this is a classification layer. right? And it takes inputs from the hidden layer. Okay? And we can add any number of hidden layers in between like this. Okay? And this is called a neural network, or in the past it's called a multi-layer perceptron, or MLP. Okay? So to learn this neural network, we use exactly the same thing that I introduced from logistic regression, because the output is just the classifier. That's the function. And the function is now more complicated. It's basically all the connections of the input and hidden layer. Okay, so we minimize the same cross-entropy loss to get the weights of the connections. Okay, and this learns both the feature extractors, the hidden layer, and the classifier at the same time. Okay, so it learns which features are important, and it learns how to use those features to perform the predictions. Okay, and we can use the same gradient descent method. Okay, in deep learning, this is called backpropagation. Okay, and it's called that because you basically have two stages. So you have your training data here. You make a prediction by doing a forward pass through the network to predict a label. Okay, and then you compare it with the true label. And if there's an error, then you will go backwards and update all the places in the network that made that mistake, or all the places in the network that caused the mistake to happen. The error signal will travel backwards and propagate to particular nodes and say, you were wrong, it's not a dog, this is actually a face. Okay, so change what you think a dog face should look like, or a human face should look like. Okay. So this forward-backward backpropagation, it sounds very complicated, okay, but it actually reduces to something very simple that you should be familiar with if you take calculus. Okay, so remember we compute derivatives to do the gradient descent. And this backpropagation is actually just applying the chain rule in calculus. Right? Because we have multiple connections, so we have functions of functions of functions, or functions of functions of functions. And the chain rule is a way to compute a derivative through all of those functions. Okay? So it sounds very complicated, but actually the math is very simple. Okay, so that's how we can learn this neural network. Okay, and then the question is, okay, how good is it? So we talked about learning theory a little bit. We want to know why this should work. Okay, what can we learn with this? So there's an important theorem for neural networks called the universal approximation theorem. Okay, and this theorem says that a multi-layer perceptron or neural network with a single hidden layer, something like this is one hidden layer, and a finite number of neurons in that layer, can approximate any continuous function up to an arbitrary error. Okay? So basically it means that it can do anything. It can learn any kind of wiggly function that you want, or complicated function. Okay, but this theorem doesn't tell you how many neurons you need to learn that function. Okay? And it also doesn't say how difficult it is to learn that function. Okay? There's a corollary to this for deep learning, which is that a deeper network, or a network with more layers, can learn the same function as this single hidden layer, okay, using less neurons or less parameters. Okay. Or put it another way, given the same number of neurons, a deeper network can learn more complex functions. Okay. So that's why we want our networks to be deeper, because we can create more and more complex solutions. Okay. But again, this doesn't say anything about how difficult it is to do this. It just says that we can do this. Okay, and then the challenge is how to actually do it. Okay, so these neural networks developed in the 70s and the 80s. The original perceptron unit was actually in the 50s and 60s. Okay, and the problem is that, as I said, it's very difficult to train. It's a very hard optimization problem, and it's very sensitive to how you start, where you started in the gradient descent, the initial solution you had. Okay, we also didn't have enough data at the time. And it's also very computationally intensive. Because the computers we have look like this. Right? So this is an Apple II, this is a Mac. This is a Commodore 64. You connect it to your TV to play games. It only has 64K of memory. That's why it's called 64. A lot of fun memories. Anyway, so because of this, it's very intensive and you need a lot of data and it's hard. Then actually neural networks became less popular in the 1990s in research. Okay, and other machine learning classifiers that people developed had better accuracy, they're easier to train, they had performance guarantees similar to neural networks, okay? And they can also be nonlinear, so nobody used them. Okay? Until around 2000, when we saw a resurgence of this neural networks, which is the phase of deep learning that people talk about. Okay? And the reason is we have better network architecture that are easier to train. We have better training algorithms and better heuristics for getting a good solution. Okay? We have faster computers from graphics cards. Okay? And we also have a lot more labeled data. Okay? So there's some websites. So one is called Amazon Mechanical Turk. You basically can go on this website and you can earn money by just doing some simple task like clicking on the face. Okay? And people have a lot of free time. So, and if they can earn a little bit of money, then it's, it's fine, and you just do it when you're watching TV or whatever. You can earn a little bit. And this actually becomes a data source for all of these algorithms. Okay, so now, because of these improvements, we can train very deep networks or deep learning. We have lots of data. We have deep networks that are trainable. We have fast computers or fast processors, and we can learn the weights of them efficiently. Okay, so that's a brief introduction to deep learning. And everything that people are doing now, right? So you see, like, we'll introduce some case studies about image recognition, face detection, object detection, whatever. It's all based on this technology. It's just modifications of the architecture to make it work. Okay, so first I'll talk about image classification. Okay, so the goal is I have an image like this, a little thumbnail, and our goal is to predict what is the object in the image. Okay, and typically there's only one main object of interest, okay, and we don't care where it is, we just care the presence of the object. Okay, and here are some examples. Okay, so if we wanted to apply our multi-layer perceptron to this problem, okay, we have an image, which is a matrix or a 2D representation. Okay, so that the multi-layer perceptron takes a list of numbers as input. So we have to transform the image into this one-dimensional vector or a vector, okay, and then we try to do the prediction. Okay, but there's a problem with this. Okay, the first problem is that the multi-layer perceptron, this node, sees all of the inputs. So that means that this node sees the entire image, and it needs to extract something from that. But we know from images that they're very structured. Okay? That means that there's spatial relationship, there's local structure in the image. Right? This duck face, or duck head, has nothing to do with this flower over here. Because in the real world, they're very far apart. They're not connected. Right? So whatever I see here is not correlated that much with whatever I see here. So it doesn't make sense to look at the whole image to try to extract a feature. It makes sense to look at local regions of the image and extract features from that. Okay, so to fix this problem, or to kind of solve this problem, people use something called a convolution layer, right, where we use the spatial structure of the image. And the idea is like this. So this is an image, okay, and what I do is I just have a sliding window here. So this is a 3x3 window, and I slide it along the image to extract a feature. And how do I extract the feature? I just use a small neural network, a small multi-layer perceptron to extract a feature. Just exactly what I showed you before. Okay. So I run the feature extractor, and it looks like this. Let me try it again. Okay. Yeah, okay. So it's sliding along, and it's putting numbers here. Okay. So this is something that a graphics card can do very well, because it's all something that in parallel. Okay. So now we can build, using these convolution layers, we can build something called the convolutional neural network. Okay, that means that we first apply a few convolution layers to extract image features. Okay, and here is an example. So I have an image. I do a few convolution layers to extract what we call feature maps. Okay, and as I extract more and more features maps, the spatial resolution decreases. Because in the beginning, what we're extracting are what we call low-level image features like corners. And in the end, what we're extracting are things like this is a face, this is the side of a building, so very high level. Okay, and then given those features, we pass it to a logistic regression classifier, or MLP, to do the final prediction. Okay. So Okay, so based on which layer you're in, it will extract different types of features. So the early layers, we say that they'll extract low-level visual features like edges and corners. So here's an example. This is the input to car. And these are the different feature maps for different features. And each one of these is a layer. So you can see here, the first set of features correspond to like horizontal or vertical lines. Okay, but if I go to the end here, right, you can see that this feature is actually, this feature is actually responding to the car itself. Okay, so this is what we call a high-level semantic feature. It's more related to the actual object or part. Okay, okay, so let's go back to our image classification problem. Okay, so in computer vision field, someone collected this data set. So this is one of the first large-scale image data sets. It's called Imagenet. It has 1,000 image classes. A lot of them are classes of dogs. I don't know why. Okay, and there's about 1.2 million images. The human performance is around 5.1% error. Actually, a human had to do that. They actually sat down and like learned all the classes, and then they actually tried to do the predictions. Like, it sounds very boring now. Anyway, okay, so on this Imagenet data set, okay, we can see the performance of deep learning over the years. Okay, so it was a contest. So this is in the past, so in 2010, using traditional non-neural network methods. So the error rate is 28 or 25%. Okay, and this is the first year that someone used the neural network. Okay, and the error jumped significantly to 16%, and using only 8 layers. Okay, and then as we go further and further, you can see the error rate decreases. Up to here, it's like 3.5%, so better than human performance. Okay, and you can see that over the years, the number of layers that we used is actually increasing. Okay, so it goes from 8 to 19 to 22, and then this ResNet has 150 layers. Okay, but it's not just that it's a deeper architecture. It's actually that the architecture, the design of this architecture is smart. Okay, and I'll show you an example of this. Okay, so here are 3 traditional networks, convolutional neural networks, that basically they just add more and more layers. Okay, the first one is called LeNet by Yan LeCun. It was for digit recognition. It only has 7 layers. Okay, and then the first network used in ImageNet was called AlexNet. It has 14 layers. Okay, and then this is VGGNet. It has 19 layers. It looks like this. They're all very similar, just deeper than each other. Here is another network in 2014 from Google. This is called GoogleNet or Inception. Okay, and the idea, the structure here looks very different than before. So if you look here, you can see it's just, this VGGNet is just a lot of layers put together. Okay, but if I go to here, if you look at this one, right, you can see actually within one layer, there's actually 4 subunits working together. Right? And those 4 subunits go into another layer and that combines information. Okay, so this is called the Inception Module. GoogleNet. It basically extracts different features and combines them together, summarizes them for the next layer. It has 22 layers and 50 convolution blocks among those 22 layers. They also added some other things. So this is the final classifier. Okay? And the problem with this very deep architecture is difficult to train because the error signal has to go from here all the way to here. So the signal, by the time it gets to this layer, is very weak. So what they did is they added these extra classifiers in the middle so that the error signal here can propagate here is stronger. Okay, and then this is the residual network, or ResNet, introduced in 2015. Okay, and this also has a smart design. So it has these skip connections or residual connections every 2 layers. Okay, and the idea of this is that what I want to do, instead of trying to keep modifying my features, what I want to do is to model or gradually refine what those features are doing. Right? So if I didn't use this layer, I would get back the previous output. And if I use this layer, then I can modify my output a little bit. Okay? And by doing this, I can have many, many layers. So they actually built a network with 1,000 layers. Okay? And they're still able to train. Okay, so these are 2 of the smarter architecture designs. Okay, and here is a comparison of the accuracy versus the speed, okay, and the size. So on the x-axis here is the speed, the number of operations, and the size of the circle represents a number of parameters or the size. Okay, and the y-axis here is the accuracy. Okay, so if I just look at AlexNet and DGGNet, so this is just the deeper version of this one. Right, you can see I can get some performance increase. Okay, but the penalty is I have to do a lot of computation, and I have a much larger model. Okay. If you look at the smarter models, okay, actually like GoogleNet and ResNet, we can get increase in accuracy, large increase, with less parameters and less computation. Okay, so we can use the parameters smarter by changing the design of the architecture, and we can get better performance. Okay, so most of the work in deep learning is figuring out how to build these architectures to work with the problem. So the architecture design is very important. Okay, so that's about image classification. So now I think in the computer vision research area, this image classification problem is basically solved. Okay, because we can get things like 3% error, 2% error, better than humans. So people started to look at other problems. Okay, and one of them is to do object detection. So the goal is to find an object in an image, which means we want to mark the box around the object, and we want to label the object. So for example, here we label this as a bicycle. Here we mark it as a car. We label it. Very useful for self-driving cars. Okay? And the simplest idea is we just reuse the image classifier that we developed before. Okay, so we take a box and we slide it over the image, okay, like this. Okay? And then we basically, for each box, we just classify what's inside. Okay? So there's nothing here. This is a duck. There's nothing. There's nothing. Okay. The problem here is that this duck is a particular shape, okay, but there's another duck here which is a different shape, which is a different aspect ratio. Okay, so we need to try different aspect ratios. We also need to try different sizes of boxes. So you can see that this becomes very tedious. Right? I need to look at all the possible boxes in the image, and then I need to apply my classifier to it. So this may take too much time. So the solution is to do something smarter. So we extract the features like before, okay? But instead of classifying every box as having a particular object, we just say, does this location have an object at all? Okay? If it doesn't have an object, then we can just ignore it when we run our classifier. Okay? And this is done using something called a region proposal network. Okay? So it takes the feature map, okay, and it just predicts whether there's an object there, something that looks like an object. Okay? And then once it has those object proposals, right, then our object classifier is applied only on those object proposals. Right? So we can save a lot of time by only looking at certain areas of it. And this makes it much faster and also more reliable. Okay, so here's an example. So here's the input image. These are all the region proposals or object proposals. Some of them are not good. Some of them are overlapping, but we will deal with it later on. Okay? We apply our classifier, and we can label all of the objects. And then people have even gone further. They can also create a segmentation or a mask of where the object exactly is. Okay, so this is how we do object detection now. Okay. The next example is about speech recognition. Okay. And the idea is that we want to convert audio speech into text. Okay. So for example, you say hello into the microphone, and then it transcribes it to say hello for you, to write hello. Okay, and this is very useful if you use Siri or Google Assistant or for automatic transcription, and also used for human-computer interface. Okay, so how do we do this one? So here's the pipeline. Here's the raw audio. It's basically a signal. Okay. The first thing we do is we try to extract all the frequency content of that signal. So at each time point here, we look at different frequency levels in the audio signal, and then we map it into this kind of image. So red here means it's strong frequency content, and blue means weak frequency content. Okay, and then for each slice of audio, each vector here, we apply a classifier to predict what was said there. Okay, so in each slice, we have a classifier, and in this case, it says H-A-T-E. Okay, so I could do this, but remember I told you the architecture design is very important. So this is a way to do it, but maybe not the most efficient way or effective way. Okay, so what we need to use is we need to use our domain knowledge. So speech is sequence data. What I say next, or the sound I'm making next, depends highly on the previous sound I'm making. Okay? And the current letter may depend on things I've said in the past. Okay? So how do I use this temporal dependence in my network? Okay, the idea is that we use something called a recurrent network, or a recurrent neural network. That means that a network has feedback to itself. So as it's listening to the audio, it remembers what was said, or what it thinks was said, okay, and it uses it as feedback to improve itself. Okay, so we iterate over each slice of audio, and we make a prediction. Okay, but we also have a state within this model, which is recurring. Okay, if I unroll this recurrent neural network and apply it to my input, it looks like this. So at each audio slice, I make a prediction. Here's my recurrent neural network, my RNN. It predicts H, okay, but it passes its current state to the next recurrent neural network. So it remembers that H was said in the past. So maybe the next thing I said was H. And now it gets to here and says, okay, you said H before, so what are the possible things I could say now? I'm not going to say C, because that's not common. I'm not going to say Z, but maybe I'll say E or A. So it's more biased to predict those things. Okay. So there are several recurrent neural networks. The most popular one is called long short-term memory, RNN. Okay, and I just briefly show you this. So this LSTM has a cell state here, which is what it remembers. Okay, and then there's different gates here that control the information that flows into this memory and come out of the memory. Okay, so there's an input gate, which controls how the presented input can affect the cell. There's a forget gate, which controls whether it should remember what it saw in the past, what it remembered in the past. Okay, and there's an output gate, which says whether the input should influence the output. Okay. And we can stack these hierarchically, so we can form, like, this is in time, but this can also be the depth. Okay. And this is very popular to handle sequence data. Basically, most people are using this now. They use it for speech recognition, for automatic machine translation, so you use Google Translate using this. Use it for text analysis. We can use it for recognizing videos or recognizing actions of videos. We can use it to analyze music, right? Because these are all sequence data. Okay, so that's how we can handle sequence data. So the final thing I'll talk about is image synthesis. So the idea is that we want to create some fake image from the computer that looks like something real. Okay, or we want to transfer the style of one image to another image. Okay, and to do that, we use something called a Genitive Adversarial Network. Okay, and this, or GAN. So this GAN has two parts. One is called the generator. Okay, so the generator just takes random noise, okay, and it does some convolutions, and it predicts an image, a fake image. Okay, and there's the other part is the discriminator. The discriminator sees real images of digits and the fake image of a digit. And its goal is to predict whether that image is fake or real. Okay. So it doesn't care what it is. It doesn't care which digit it is. It only cares whether it's a real digit drawn by a person or a digit synthesized by the computer. Okay. And the interesting thing is that these two pieces, the generator and the discriminator, they're trained against each other. Right? So the generator is trying to fool the discriminator to make it think that it's producing real images. And the discriminator is trying to guess which one is from the generator. Okay. And the training actually finishes when the discriminator is fooled. You can't tell the difference between a real and a fake image. Okay. And that's how the images will turn real. Okay, so here's some example of it. So this is an example using style transfer. Style transfer using something called CycleGAN. So you can convert paintings by Monet into real photos, or you can convert zebras into horses, right? Or you can take a photograph and you can apply a particular style by a painter, like this. Okay. So when you use, I think Skype has this built in, or maybe Facebook also, or Instagram, they have these like filters or whatever. So you can also, that's based on this. Okay. So you can also generate face portraits. Okay. So this is using something called StyleGAN. Okay. Here are some faces. So my question to you is, which one of these faces, or which faces do you think are the fake faces? You can take a look first. Let's see. Okay, so who thinks the first face is fake? Okay. How about the second face? It looks real. Third face? People. The fourth face? You don't think this is a real person? Fifth face? This one has some weird hair over here. How about the sixth face? Looks real. Okay, so here's the answer. Actually, 1, 2, and 3 are 1, 2, and 5 are fake. This one, like you can see, there's an earring here, but not an earring here. A little bit weird. This one, I don't know what this is, but if this is a real person, you probably want to get this checked out. This one, like I said, the hair here just looks weird. It's like hanging out there. I don't know. Okay, but actually, all of these faces are fake. Right. Some of them are actually very impressive. Okay. So if you want to try this out, there's a website that you can actually just generate fake faces and look at them. So you can try it out. And that's all I want to say first about the deep learning. And we can take a break now. You can try this out and rest. And then Cong will talk about security. So let's take a 10-minute break.
Let's invite Dr. Wang to share his views on machine learning and data privacy with us. Dr. Wang, please.
Thanks for the introduction. So I will just follow what Antoni just mentioned, machine learning, but I'm going to talk about more from security, privacy, and even robustness perspectives on these machine learning systems in practice. I think we already know machine learning is changing the world, and many of the tasks that these machine learning systems are doing very well in their I would say in their application-specific settings. But on the other hand, there are some applications from machine learning that needs to deal with not just the limited settings, but actually the so-called open settings. And for example, autonomous driving, and we all know it's receiving a lot of attentions, is on a rising trend, but still is not performing as what we expect them to perform so far. And there are reasons behind that. I think on the one hand, it could be still there's some algorithm or we still lack of large amount of data for training these autonomous driving systems. But perhaps on the other hand, there are also sometimes, say, attackers or adversarial, they might come up with a new special input that might somehow trigger this machine learning system to behave unintended. And one such example could be, for example, in such kind of simple adversarial environments, people can simply use a bottle of salt and to draw a line to simulate what the traffic lanes might look like so that they can trap autonomous car. So this could be one example that bad guys can do some simple things to trigger the system to behave in unwanted fashions. And there are also other scenarios. For example, you can simply use biased data input to train machine learning bot, and then to teach them how to do, say some bad languages in terms of something that we don't want them to learn. It simply is more on the data bias issues or ethical issues. You can teach them in one day. So these are just some simple examples that I think machine learning is still facing a lot of challenges, not just on accuracy, correctness, or how to solve the problems to replace human intelligence. On the other side, we also need to deal with these adversarial settings. So in the next few slides, or next talk, I'm going to talk about this machine learning systems, security, privacy, and robustness aspects. And I'd like to use this example to demonstrate. We'll first talk about the data parts. So if we consider machine learning is very complicated, of course it's not as complicated as rocket science, but still I can use that as a simulated example here. It needs engine or model, which is the algorithm design or the network architectures. So as Antoni mentioned, architecture actually matters a lot when you solve different problems. On the other hand, we also need to deal with the data. And there are problems related to the data as well, especially the privacy issues. So we talk about that now. So actually, in the past decades, I would say, many of those tech companies, especially big names, they're all trying to find out new ways to monetize their customers' data. And there was a saying back in 3 or 4 years ago that the world's most valuable resource is no longer oil, but just data, or your customers' valuable data. So their way to do this is to find all kinds of free services to their customers in a way to exchange for their customers to provide data, and sometimes well-labeled data. So as Antoni just mentioned on Facebook, right? You get the photos, you need to label the photos for Facebook, although you think you label it for yourself, for your friends. But at the same time, Facebook uses those well-labeled data to do the training and learn more about you. So from privacy aspects, I think we can zoom into to see what kind of policies behind those service providers. For example, on Facebook, it says clearly that we're going to create personalized products that are unique, relevant to you, based on using or learning or mining your connections, preferences, basically user profiles. So that's what Facebook does. The kind of collect the data, trying to monetize data, sending you targeted ads. Also, on Google, like a voice assistant, sometimes to basically understand your voice with recordings, they have to send those information back to the Google's backend and to do the kind of recognition of the voice. And that basically, they get the data back. We collect the data to the backend. So, of course, you need to trust them in good faith that they're taking care of the data. But that's not always the case, because once data leaving your device to somebody else's hands, you lost control. All right, you lost control. So this, and there is another famous app called Meitu. People use this to maybe add good effects on their selfie photos or whatever other photos. And also they take back your data. Once you upload a photo using your app, you use the app to get some effects on your photos. Many of the cases, those apps send the photo back to the servers, and including everything on the photo, containing the photo. So as I just mentioned, we are using this for free, and we also trust the service providers to take care of our data. But in reality, still bad things might happen. For example, this is the famous example, like Facebook failed to control, or some of this Cambridge Analytica to build an app on top of Facebook platforms somehow to steal or to retrieve in an unauthorized fashion billions of user social profiles and use that for influencing online opinions. Right? It's still happening today. Even today, in this round of elections, still people worry about whether Facebook might be a kind of player to influence the people's opinion online. Another example, like for example, Google, this is recent news, somehow admitted that more than 1,000 sound recordings of customer conversations got leaked through some of these partners. So I think in practice, when the data go to those major providers' data servers, they also have other contract deals or collaborations with their other third-party data brokers or other third-party service providers. So it's really hard to control whether the data is in the wrong people's hands or not. Okay, and of course there is some people just advocates like this. There is basically no control or few control on how your data, including your face data, I mean this is from Face app, I think, will be used once you send your data to the servers. So this is one of the concerns that although, one of the concerns that even though we know machine learning is doing very well, but to fuel this machine learning giant system to work very well, we need large amount of data. So we need to feed the data to those companies to train the models. But there are also possible privacy concerns. So is there any other ways that researchers or those IT companies trying to find ways to address these problems, because the privacy or security concerns is on the rising trend as well. So number one thing people may think about is, how about anonymize my data? So I just publish maybe I can send you my recordings, but remove my name, remove my personal ID information associated with this kind of voice recordings. Would that work? Well, there has been a long line of research showing that anonymization, this kind of efforts, if you want to rigorously define anonymous, is very, very hard. It's always can, for those for attackers or for adversaries, they can leverage some background knowledge, because nowadays there is on the internet, your footprints, the digital footprints everywhere. So they can always leverage this online information, collect the background information, and try to use those anonymized data, re-identify who this data belongs to who. Therefore, this line of efforts is still ongoing, but I would say anonymization to achieve truly anonymized data publishing is very hard. Okay, so we have to face the reality. The privacy issue is still there, especially not only just from the customers, users perspective, but also from the law enforcement perspectives. So I think maybe many of us have read similar news like this. This is the GDPR, the Europe version of the data protection regulations, which is in place back in 2018, 2 years already. There are other similar, more rigorous data privacy regulations being deployed in place all around the world, including mainland China. More and more stringent rules are already in place. So that's the requirements on that. However, right, so how to interpret those privacy regulations is very hard. Right? Different people have different opinions, so they may wonder, because it's not standardized. Even today, we don't have a standard say how to deal with your data, especially in the machine learning context. So how do we collect the data while complying with privacy regulations? This is, I think, from the security point of view, this is actually a very hot problem. All people are trying to find new ways to propose it, or maybe try to standardize practice, so hopefully all the industry will follow. To respect people's privacy, but at the same time enable the machine learning training or inference tasks. So in the following, I'm just share with you maybe a handful of trending efforts that's trying to solve these problems. And the number one could be so-called you train on your own device. So we know machine learning, to make it work, you need data to do the training. And in the past, we need to collect the data from all these users here and pull data to some kind of data center or the cloud to do the training. But then that somehow violates the possible privacy regulations, because now you collect the data, raise the concern. People may worry about, are you taking care of my data or not? All right. So perhaps we can do it in the other way around. In order to do the training here, we can distribute computational training tasks to each individual data holders in a way that you push the task to them and ask them to train on their own device. Once they finish the training, they're going to make some model updates. It's just, Antoni mentioned some linear regression, regression, or deep neural networks. Once they train on their own data, you can send their model back to the sends the model back, not the data. So the data never leaves your device in this practice. And then this central server can aggregate everybody's inputs on the model, right? And then they try to do certain kind of aggregation, and then iteratively sends back these aggregated results back to the individual devices and asks them to do the training again. So it's round by round, iteratively do the training. So you can see throughout the whole procedure, data is always kept at each participant's devices, not on the central server. So there is no data collection points here. As in a way, we still try to address the learning or the training problem, and we need a lot of data inputs, so we can do it this way, but somehow we don't have to collect the data anymore. Okay, so that's one of the proposals to address this problem. And indeed, if you use an Android device, actually on your Android device, your Android keyboards, they have so-called recommendation on your typing based on typing habits. That's already been utilizing this kind of training and kind of make your life easier in terms of when you use the keyboards, you're typing the keyboards, and somehow you type the first key, the second character automatically show up based on your own typing habits. But at the same time, it's also gaining the benefits by somehow the model trained from other people's keyboards. Okay, but in a way, you don't have to share across each other's the data. So that's one of the example here, and of course, the same intuition we can generalize it to other application scenarios. For example, smart health or hospital disease modelings, where patients' data can be very sensitive. No one wants to share those patient data across different hospitals. We can do this kind of training in a distributed fashion without violating the privacy regulations. Okay, but of course, this is just still, I think, proposed back in the 3 or 4 years, still an ongoing phase. There are many challenging issues, efficiency, correctness, all those kind of things that we need to deal with. And especially, what if there are some dishonest participants? They do not trade. They can participate in the free rider fashions. They never contribute their data or contribute their computational resources, but somehow they try to still gain the benefits by playing with everybody else. So all these are the issues that are yet to be addressed, and this is some of the ongoing research efforts on this direction. So this is one of the ways that somehow we can train without relinquish the control of the data outside your device. And the number 2 efforts also trying to, along this line, could be so-called encrypted machine learning. So this might be a little bit advanced. It's more on the theoretical side, I would say. So this idea, the proposal the research has been actively researching about is, we all know encryption helps to protect your data. But sometimes we need something not just protect the data, but also protect the data while still enabling certain operation on those encrypted data. So in that sense, we call it advanced encryption techniques. And one of the examples could be named homomorphic encryptions. I think it's been proposed more than 2 decades, and the development along that line has been a lot, especially more than 10 years ago. In theory, for the first time, researchers have already shown that on paper, we know how to encrypt a piece of data. At the same time, we can do arbitrary function on top of the data. And that means now, in theory, on paper, we know how to do encrypted data and then do the machine learning training directly over the encrypted data without decryption. Okay, then we can achieve this encrypted machine learning without violating any of the privacy regulations. But of course, there was always a catch. The catch is still on paper. In theory, we already have the breakthrough. All right, just like many of the research areas, on theory, we already know the breakthrough. Now the problem is how soon can we use it in practice? So far, still have a very slow efficiency, and there's some limited amount toy examples, and you can have a sense. If you ever have any hands-on machine learning training tasks or inferencing tasks, you can see a comparison that these very small scale problems, we do it in the order of maybe half an hour, or even much more than that. And for all the tasks that in the first half of the talk about Antoni just mentioned about image recognitions or voice recognitions, what we need could be millions or billions of data, not just this small amount. Okay, so you know kind of a comparison between the two. Still a long way to go. So that's the second effort. Try to do it in a privacy-preserving way. And so the third one, which I'm going to talk about, is called hardware-assisted approach. This seems more promising in terms of performance, but the only thing that we need to sacrifice is we need to trust the hardware manufacturer. Okay. So what this means is, in order to make machine learning training over those data in a secure fashion, somehow your data never fall into the wrong hands, we can also utilize this hardware and so-called secure enclave to build a secure, isolated region where you can just push your computational data and your program into that secured enclave, so-called a region, where you trust the hardware is perfectly designed, that no one unauthorized can see through what's being inside the secure enclave. And then you can do the machine learning training inside without worry about data break. So on your phone, again, I'm going to use the example on your phone. You already have secure enclave in place. It's a very small piece of storage. that kind of protect, for example, on an iPhone, protect the Face ID or your fingerprint data informations. No one can get access to that piece of information except that hardware piece, okay? Except the hardware piece. So in that sense, even if on your phone or on a computer, there are some other malicious apps, or maybe the phone falls into other people's hands, for example, still no one can break through to see what's inside the secure enclave region. And then as long as that region you consider is trusted and unbreakable, secured by the hardware, then you can just feel safe to just push into your encrypted data model and do the encrypted result through the training. But of course, there are also challenges, because so far this secure enclave is not powerful enough, like GPU, like what we have data centers to do computationally intensive tasks. So we can only do small-scale problems, but not the large-scale problems. But still, there are ongoing efforts to try to see we can leverage this kind of latest hardware-assisted secure computation architecture to do more data-intensive tasks. Okay. So all these are about ongoing efforts related to machine learning practice, where we do not want to sacrifice your data privacy, at the same time want to enable machine learning training. So related to the data privacy aspect, there is another side of research people have been working on, is maybe, or I would say security researchers would like to show, is can we use machine learning tools to somehow to invade person's privacy, especially in settings where normally people consider there's no security risk at all. One example could be we're all using these video streaming services like YouTube or Netflix. So when you watch a movie, usually what happens is you establish from your phone or browser to the remote computer. There will be a secure encrypted ongoing network session, which is usually can be seen by this HTTPS on your address bar of your browser, or there is a simple lock on your browser. That basically means this is end-to-end encrypted. No one can see the traffic content. All they can see is a piece of data packets somehow in random streams, because it's encrypted, passing through back and forth between your phone and the remote server. However, if you understand how encryption works, then encryption just translates a piece of plain text data into a ciphertext data, a random string, but it preserves the packet size. So if you have a data with 100 bytes, after encryption, it's more or less 100 bytes. If you have the data with volume very small, and then later on volume very large, after this kind of encryption, the ciphertext, if you look at the ciphertext, still they can tell this is a small piece of chunk of ciphertext, and there is a large volume of ciphertext. So all these things got preserved. What do we call that? As traffic pattern. Okay. Now, interesting things here is for each individual movie, their traffic pattern can be unique. For example, you watch this Beauty and the Beast, right? And if you compare that with another 007 movie, I would guarantee you the traffic pattern will be always unique. Then you can build a simple classifier using machine learning techniques, which Antoni just mentioned, which regression. And then by looking at the two traffic patterns, you can classify which movie are you watching, although we're establishing the secure communication channel. Right? So this is something people are trying to demonstrate, so showing that machine learning tools are actually very powerful on these aspects. So that's pretty much about the data view aspects. So the privacy aspects on data. Now I'm going to talk about a little bit on the engine part, on the model parts, and how reliable or how robust this engine can work. So back in 1950s, 1940s, there has already been this pioneer, this guy named Alan Turing, in case you don't know him. The top computer science award is named after his name, called Turing Award. Right? So this is a guy, he proposed a test for you to test whether this machine is intelligent enough. How to do that? Well, or whether this engine works well, right? So basically, you have a curtain. Behind the curtain, you have two. One is a person, a human. The other is a machine. It's always we need to compare the performance of the two, right? And you ask them a question, and ask them to give you an answer. And based on the answer, can you tell the difference? Well, which answer comes to human, which answer comes from this machine? If you cannot, then basically this machine learning system is very intelligent, right? Or even in some sense, it outperforms what a human can do. Okay, so this is the standard Turing test about that. So in other words, machine learning model should be as reliable as human. Okay, but of course, when we state this statement, we want to make sure that this is based on arbitrary input. Any input, machine learning model should be as reliable as human. But is that really the case? Or show. So come back to this simple neural network training tasks, where we want to train the network to learn which one is cat, which one is dog. So we feed in the training data like this. And so hopefully after a while of trainings, we present something like this. This model will recognize this looks like a cat's face. So this is a cat. And present something like a dog's face like this. Even if it's a cartoon, we want this model to recognize it's a dog. But possibly, through the training, your data can be biased, right? Or maybe the machine can learn in a biased fashion. For example, all the cats are white in the training data sets. So perhaps if you present a white dog like this, he will also learn it's a cat. Maybe it's insufficient training data samples resulting from this. So it's possible like this. Okay? So after the training, let's see what will happen. If you present a cat in black, then it's likely, I'm not saying it's definite, but it's likely that the model will consider this as a dog because it's black. Because somehow this is due to the lack of data training or due to the insufficient lack of data bias issues, there is a problem. And it's also possible that even if you present a white cat, but you add a black pixel there, all right? I mean, it's still possible likely to introduce a small error somehow got propagated in this neural network and eventually amplified. And when you reach these classifiers, you consider that as a dog. So it's possible. I'm not saying it's always the case, but it's possible. Okay? So this is behavior raised the question that people will always ask. Maybe in the learning theory, people ask, do neural networks really understand their tasks or not? So that's actually the motivating question that triggers people to try. Well, if I'm an adversary, can I generate a photo that human will tell no difference with a normal photo, but somehow always cause the error for machine learning to make? Is that possible? So that's the question people are trying to raise. Again, it's about robustness issues. And indeed, people find a way to do that back in the 2014. All right, so this is a panda photo. We all know it's a panda. And we can add a small piece of noise, all right, just on the per pixel wise, add on top of the model image. So the result would be still in human's eye is panda, always panda. But if we present this picture on the right-hand side of the equation to the machine learning, well, it will consider that classified as a gibbon with confidence level almost close to 1. Okay, so this is intentionally or adversarially corrupted samples that with the purpose to not triggering errors for human, but triggering errors for machine learning models. So this is what we call as adversarial examples. So this is another patch. So we see this is a banana, and there's a classifier output. Now, I already embedded a YouTube video here, and you can see that people are trying to introduce some change to confuse the learning model by first inserting, this is the toaster, nothing changed, classifier still banana. Now he's inserting a special input. It looks like strange. I don't know what it is, but there's special colors on that. As you can see, immediately this classifier got a wrong output, saying this is a toaster. All right, so this is intentional targeted misclassification attack by presenting some adversarial input to the machine. Okay, of course, in human's eye, it's still a banana in the picture, but then in the machine's eye, it's changed. Okay, yeah. Anyway, so what happens here? Well, the problem here is So this is a nonlinear classifier, which I think Antoni just mentioned how we view this nonlinear curve to classify the points in the space, right? And then we all know this boundary when you draw to do the classifiers is not always perfect. There always have some corner cases. And then the adversary's goal is to find those corner cases and introducing small errors or shift of those data points. And then in a way, in the human's eye, there is no problem at all, but in the machine learning's perspective, then it's going to make a wrong decision. For example, you can add a small error on these points, change it to here. So in the human's eye, still within the dotted line, it's a natural input. So everybody can see it's correct. But then in the machine learning's point of view, it's got changed from a cross point into something outside the boundary, which is considered a circle. Okay, and what makes things worse could be we have multiple layers in these deep learning models, and so that's why even you introduce a small amount of error on input, this error can be amplified through the propagation of these layers. In the end, it will be propagated into so large effects that somehow trigger the error to the machine. So what a human eye sees is this picture, but what machine make decision is after propagation of errors, you make decision here. So that's why it's possible to do this attack. Okay, to do this attack. So now let's see what's the effects that might be used in today's practice. So in MasterCard, so payment systems, they already introduced so-called identity check that you can on your phone, that at the same time using your face or iris scan, whatever it is, or fingerprint to do the authorization of some payment on your phone as a second factor. So using biometric as a second factor to authorize certain actions by scanning your face, for example. But of course, then some researchers shows that I can fool not all the face recognition systems, some face recognition systems, simply using glasses by introducing small errors or small perturbations on the input face. So the first, on top of a row, these are the attacker's presented image. And then the result would be totally different person. That machine will consider wearing a glass or not, it will change to a totally different person in the eyes of, or in front of the machine learning systems. Okay, so this is what the attackers try to show here. So you can do something bad, and then maybe you can try and make fraudulent transactions. Or physical world, we all know this is stop sign. When the car sees a stop sign, you have to stop. All right, but then attackers shows in the physical world, I can just add some funny stickers on the stop signs, so that autonomous cars, in their kind of when they read those signs, they will be confused and read them, consider that this is always speed limit 45. I don't have to stop. I can just drive with the top speed up to 45 to continue driving. So basically to fool those machine learning decision making. All right, and then that cause accidents possibly. And even on audio, all right, the same audio, you add a small amount of noise, you will basically be translating to different things. So we can listen to this audio first.
Without the data set, the article is useless.
So I guess you know it's just a sentence, right? Without the data set, the article is useless. Now let's listen to the adversarial audio samples here.
Without the data set, the article is useless.
So still the same, but now you will consider something else. Well, if you presented that to a machine, I say, okay, Google browse to evil.com, which is a malicious website, which containing some phishing content there. And then that could be the stepping stone for other advanced attacks to compromise your phone. Okay, so you can see this is very a lot of research efforts on these aspects to try to adversarially interrupt the robustness of the machine learning models. So you can even corrupt these samples without expert knowledge through automated tools, open source projects online. So how to deal with this? Well, it's still an unsolved problem in my personal view. Perhaps I have different opinions, but in my personal view, I think in the past 5 or 6 years, you can see the exponential growth of paper on this area, more than 1,000. No dominant solution so far. It's becoming a game between the cat and mouse. You have a more advanced defense, I have a more advanced attack. Always can find adversarial samples. So back to that question, what is this picture? Panda or Gibbon. Seems like you're always using this adversarial sample input to differentiate whether it's a machine or a human. So I would say still a long way to go for the intelligence of machine learning to catch up with human, in some sense. Or still a long way to go to make machine learning system to be robust, or as robust as possible. Okay, so that's the data parts on privacy and also the model parts on the reliability or robustness. In the next, I'm just going to quickly go through some other examples to show other security or how to spoofing the machine learning to do some to trigger this machine learning to do something unintended. Okay, so if we look at this machine learning system from a computer science point of view, it's just a complete system that take input from the physical world. That could be sensors, right? Microphone or speakers or microphone or video cameras, etc. And then we change them, translate into digital formats, and then we take the feature, feed it into the machine learning model, and make decisions. So this is the whole flow where you feed in the data and you get the results. And indeed, attack can happen on any parts of this complete data flow here. So previously, all we mentioned is something here, protecting the data or disrupting the machine learning models. So actually, attack can happen here as well, okay, on the physical sensors. For example, there are researchers showing that in terms of looking at this system software, right, we have all kinds of dependencies, framework, and apps that constitute a full-fledged machine learning system that running on top of a lot of softwares. So many of these might have so-called bugs or exploits lying, hidden inside their code level. So some of the researchers shows that by scanning through this, all the dependencies, frameworks, and software bugs, they can find or construct special inputs to raise for different purpose, of course, adversarial purpose. Number one is they always use the same original image like this, a bulldog. So if you present it to this machine learning model, you will recognize it's a bulldog. Now, the second try, add some effects on input. So still, in human's eye, it's a bulldog, but now it's creating adversarial effects, change that to cats. So this is some example, some adversarial effects I just mentioned about. The third case, this is another malicious input. Now when you read that input, open this picture on the app, your app will crash. Right? So basically this is some memory flaws that people have found and hidden in the input to trigger the memory corruption attacks. Memory crash, crashed. So your application got crashed. So if you ever did anything on computer security, you know when you have application crash, that usually have some implication showing that you can leverage this input to generate an exploit to take over control of the device. And indeed, that's what the attacker does. Shows the final try is I can just feed in this input to your apps. Now, assuming your system is with flaws, right? He can find this malicious input inside that image, sent to the device, and eventually root the device. Root the device means take control of the device. Okay, so all based on a simple image. So this is an example on that. And so let's move on to look at some other advanced attacks, so-called sensor spoofing attacks. Okay, sensor spoofing attacks. Now recall that the machine learning system, they need to read signals from the physical world, okay, through the sensor. All right. So think about this scenario. You're sitting here on a chair, having a conversation. Somebody shout to you, say, "Hey Siri, transfer some money to me." He might arise the Siri, right? Activate the Siri on your phone. I haven't tried that, but in the classroom you can try, "Hey Siri," perhaps some of the phones, "Hey Siri" will be activated, and then some of the command get passed to the phone. But the happy ending here is if somebody shouted this command to you, you will notice that, and you probably will call the police. Okay? So what if somebody is whispering the other command, but somehow you cannot hear that, but your Siri can pick it up? Would that be something alert? And indeed, that comes back to so-called the voice signal's frequency, so the frequency band, how wide it is. We all know in humans' ear, this is what we can hear. from 20 hertz voice to 20K hertz. Anything beyond that, we cannot hear. Right? And then this is what dolphin can hear, from 150 to 160K hertz. Right? So they have a very nice ear. Maybe dog also have something that can hear the sound in the ultrasound band area. How about Siri? Well, it's not exactly matching the human's acoustic band here. It has some extra window here. So which means if you send a command here, both the phone and the human will catch it. But if you send a command here, you will ignore that. Sorry, not ignore. You will not be able to pick it up, basically. This is something you cannot hear, inaudible, right? But your Siri will still pick it up. And they will do the command. So this is called a hidden command. Or some people just name it as a dolphin attack. Okay? Because they notice that the sensor can be spoofed, simply because the sensor can pick up some information that your human cannot pick up. This is published in one of the recent papers, recent security conferences on that. So similarly, following or motivated by this kind of idea, we can spoof the sensor in other formats. And indeed, very last year, people have shown that on your smart speaker, like this one, it's supposed to pick up voice command. But then, surprisingly, researchers show that I can use a laser points to point into the speaker. And I can still send a signal to the speaker in a way I can embed certain hidden command. All right, so this is like send commands to your voice assistant using light, using exactly laser points. The reason behind that is, of course, in the physical sensors, those microphones, they can sense light signals. If they can pick up the light signals, then you can embed your command hidden in the light signals, and then to trigger the speaker to listen to your command. Okay, so without making a sound, you can still trigger the speaker to do. So this is the spoofing sensor attack. Another thing, this is easy to understand, right? People always think about, I think the intuition is very simple, how so-called poisoning attack. So recommendation systems, so again, as Antoni in the beginning of his talk mentioned, when you open up Google or eBay or Amazon, you always enjoy the benefits of these recommendations. You visit certain products, they're going to recommend other products to you because they think you are similar to the people buying this, so they think you can buy other things. Recommendation. So normally this is what we do in the machine learning settings. If you visit a brand, on the website, suppose we're visiting or click on the ads, all right? On the websites, you click on McDonald's, and at the same time you also click on KFC. And then a new guy comes. He views the ads of McDonald's. Then most likely that website will recommend KFC to this guy. A so-called co-visitation, recommendation. So this is feeding information here. Now, of course, security researchers shows, well, if this is the mechanism of how you do the recommendation, now, can I hijack this? And the result is yes. I just create a lot of fake users or the bots and go to the online, click on these two ads. The first ad is the ads McDonald's. The second ad is the ads that I want to feed into your view later on. So for example, there is another brand name, KLC here. So I can create a lot of fake users, doing this both with co-visitation simultaneously. It's like creating a lot of poisonous, fake biased input to the machine learning system. All right, so teach them bad experience. In the end, it's like now the machine learning system will know that if you like McDonald's, you must laugh something I want you to laugh, because those fake users have been feeding quite a lot of malicious or poisonous inputs to the system. So the idea is very simple, and you can simply, well, ethical issues come here, but for research purpose, you can simply just repeat this practice and demonstrate this actually works in many of the websites, feeding ads. And then you can generalize that to many other examples. Any brand, you can just do this targeted attack to do that. Okay, so the basic concept here is some people dab it as garbage in, garbage out. So whatever you teach the machine, because the computer learns from the past experience, they will repeat or possibly recognize that. So whatever you teach them, if this input is biased, they're making opinion biased way. Okay, so perhaps that also comes to the ethical issues. So finally, I would like to talk about something else, the unintended memorization. So again, this is an example Antoni just mentioned, Smart Compose in Gmail. Whatever you input, you finish the first half of a sentence. Gmail will recommend you, okay, you're going to say something else, right, to propose this to you so that you can hit the tab on your keyboard, saving the typing, tedious typing here. However, again, researchers show that in some extremely bad settings, all right, it's possible to complete, well, to leverage this autocomplete feature to retrieve some sensitive information. I'm just using this toy example here to show, although we don't have time to zoom into the details. But what this means, if you enters Alice Hong Kong ID number is, presenting this autocomplete machine learning model here, it's likely that he's going to tell you exactly what's Alice Hong Kong ID number because it's trained part of the training data sets. Okay, something like this, following this, because autocomplete on the one hand is give us convenience, but on the other hand, in some extreme bad settings, there is a chance for attacker to retrieve the secret information that's buried in your training data sets and possibly trigger that through some hidden input here. So to conclude, now, how much should you trust the machine learning system? So people don't know about AI. They always argue about AI will take over the world. I hope after today's lecture, you have your personal opinion. Maybe it's different because they cannot even answer this question, right? Is it a dog or a cat? It's hard to say. Okay. So I think I'd like to conclude my slides is machine learning community always working on how to build it. Efficiency, accuracy, I think that's very important even today. We're still solving a lot of challenging questions on that domain. On the other hand, a security community always want to see how to crack it, but it's not for the purpose of cracking, it's for the purpose of how to defend it, making it more safe. So for that, I'd like to conclude. Maybe Antoni will conclude, and then we'll follow by Q&A sessions.
Yeah, so thanks, Chong. So I'll just talk a little bit about some further challenges, not related to security, but in terms of how we use machine learning, and also some future opportunities for you guys. Okay, so Chong mentioned this a little bit about dataset bias. Okay, so the machine learning model is only as good as the data you present to it. So if the dataset itself is biased, then the model will be biased. So it will focus on things that it sees more frequently. It also cannot learn what it cannot see. Okay, and one example that recently appeared is from this article in New York Times. So most of the face recognition systems are trained on data sets with Caucasian faces, Western faces. Right? And if you apply these algorithms to African American faces or even Asian faces, then you'll get misidentified. Right? And also, right, if you present women rather than men, you will also be misidentified. That's because most of the data sets are predominantly men. Right? And if you use older adults, you will also be misidentified compared to middle-aged adults because the data set doesn't have older adults. Okay? So these are some challenges that we need to think about when we use this in a real situation. Right? Okay. Another problem that we have, which is related to the adversarial attacks, is the idea of whether the machine learning model can be explained or interpreted. Okay, so the deep network is very complicated. It has a lot of parameters that we need to do. And in research, we consider this as a black box, meaning that it does something, but we can't see inside to see how it's working. Okay, so whether the model can be explained or interpreted is important in some situation where there's real-life consequences. Okay, so for example, if you apply for a loan at a bank, right, the bank will collect all of your information, your salary, your background, how often you smoke, whatever. Right? Whether or not you get that loan depends on the algorithm that looks at that data. Right? And if that algorithm can't explain what it's doing, then when you get denied the loan, you will ask, why did you deny my loan? And the bank, what will they say? Well, if they can't explain the model, they can't say anything, then you challenge them. Okay? So we need to be able to describe what was the decision process in order for you to deny this thing. Right? Another example is in self-driving cars. So there's several self-driving car accidents. We want to know why did those accidents occur. Right? And if the model is a black box, you can't do that because you don't know where the model failed. Was it the data? Was it something wrong with the programming? Was it something wrong with the architecture? Right? And if we can identify where the problem is, then we know who to blame. Right? So then also tells us how to deal with these kind of accidents. Okay. The final challenge is that most of the things that we do now, we need a lot of data. We need millions of examples. Right? And this is great for generic tasks like object detection or whatever. Right? But if we want to apply this to very specific tasks, for example, I want to detect some kind of medical disease from a CT scan or CAT scan. Right? But I only have 5 examples of this. How can I train a machine learning model on this very limited data to work? Okay. So there's several ways of doing this. One is called, and they're all related. So one is called zero-shot learning, which means that we learn from a description of the problem. So I say a cat should have ears, whiskers, it should be cute, and it's both white and black. Right? And from this description, you can infer what it looks like. Okay? This is what humans can do. Another is one-shot learning, which is you just present one example, right? And the machine can infer all the variations of that example. A human can also do this. Okay? And another is called meta-learning, which means that we, instead of programming the computer to learn, we program the computer how to learn to learn. Okay? So this is an example. So we have a data set, which is a meta-learning data set, which contains different tasks, the training and test data. And instead of just training the neural network, now what we're training is the thing to train the neural network. Right? And you can think about it as we're training the gradient descent algorithm to be more effective. Okay, so once we've created this trainer is good at training a network at different tasks. Okay, then I can create a new task, and I can train my network by using a trainer that's designed for the other task and can generalize the new task. Okay, so this is called meta-learning. There isn't a learning to learning to learn to learn yet, but maybe soon there will be one. And this is actually, how humans behave. Right? So this is kind of like you present a new task, you know how to deal with the task because you've learned how to do it. Okay? So those are some of the other challenges in terms of the data and explainability. And now I'll talk about some opportunities for you guys. Okay, so one is this interesting figure. So this is the average base salary in the US for different tech jobs. Okay? And at the very top, the 3 out of the top 4 are related to machine learning. One is computer vision engineer, which is just machine learning applied to computer vision, to analyzing images. One is an actual machine learning engineer. Okay? And another is a data scientist, which is applied machine learning. Okay? And these are the top 3 jobs, okay, in terms of pay. And you can also, in the same article, the increase of demand for machine learning engineers increase has been 300% over 3 years. Okay, so these jobs are becoming very hot, right? And the reason is because there's not a lot of people trained in these areas. So people like Google and Facebook, they start to pay a lot of money for very good research or very good engineers. Right? Some people, they will get $1 million US dollars to work at Facebook or Google because they're like a star in it. So this is, so if you can see that it's very, big demand. Okay, another thing is in terms of the opportunities. So this is called the machine learning pyramid. Okay, and the size of the triangle is how many people there are that can do. Okay, so at the top are the researchers who can create the new algorithms, okay, and then there's engineers who implement them. The data scientists are people who use machine learning to analyze data. Okay, and the final benefactors are actually businesses. Right? So, there's not a lot of engineers or data scientists, but there's a lot of businesses. Right? And a lot of businesses are interested to use machine learning to look at their customer profiles. Right? If you can analyze a customer profile, you can suggest things for them. Right? You can find problems. You can find new sources of revenue through machine learning. Then that becomes a bonus for them. Right? They can increase the size of the company. They increase the profit. Right? And if you look at Hong Kong, so actually out of 100 companies in Hong Kong, right, in past, this is survey done 2 years ago, so in the past 2018, almost half of them have some initiative in machine learning or artificial intelligence, meaning they want to leverage their data somehow. And the problem is that there's not enough engineers. That's why they have high pay. Okay. So I hope I convince you that this is an interesting area. And if you want to know more about this area, it's actually very easy to pick up. Okay, so moving forward, so most of the deep learning, machine learning software is open source. That means that you can download it for free. That means that there's tutorials and blogs people have posted to teach you how to use this. Okay? And the implementations of many of the models and the models themselves, the trained models, are available on this website called GitHub, which is just open source repository. Okay? So if you're interested, you can go and look at this. Right? There's also many MOOC courses, online courses that you can take to get more formal training about machine learning. So one of them is by Andrew Ng, who's a famous machine learning scientist, researcher, by Coursera, and there's also a deep learning version of this one. Okay. Another thing that you can use is this idea of cloud-based machine learning. So the problem with doing deep learning is that you need a GPU to train the model, which means you need hardware. Okay, and what Google and Kaggle have done, Kaggle was bought by Google, so what they've done is they actually create environment for you to develop machine learning algorithms and deep learning algorithms that you can run in your web browser. Okay, and what it does is it collects to their own server in the cloud and runs those algorithms for you. Okay, so you don't need any specific GPU hardware. You can do it directly on your laptop. And all the computation is actually done somewhere else for you. Okay, and this is called Google Colab. It's a very nice interface. And there's another one called Kaggle Notebooks, which is, Kaggle is a machine learning competition website, and Notebooks is their way of publishing code. Okay, finally, if you want more hands-on things with machine learning, you can use this product called Google AIY. AIY is it's like DIY, do it yourself, but it's AI yourself. And they have two of these little AIY projects. One of them is a speech recognition project. So there's a speaker and a microphone, and it's basically like Google Assistant, but on in this little cardboard box. Okay, and it's running. It's using It's using a small board. I forgot the name of it. Yeah, but it's an open source board also. Okay, and the other one is a computer vision AIY. So there's a little camera here and a button, and you can actually take pictures with it and analyze the picture to detect the face or to detect like the facial expression or the happiness of the person. Okay, and this is actually interesting because it has a small chip, which is like a very small GPU that runs very fast. It's something that they developed. Okay, so finally, to conclude, so we've talked about machine learning as a way to give computers the ability to learn a task. Okay, and we also showed some examples of deep learning using neural networks and showed that the architecture is important to adapt to different tasks. Okay, and Cong talked about how to, the problems with machine learning in adversarial environments. Okay, and here the real issue is that as we trust the machine learning to do more things for us, right? I ask Siri to do things for me, to set my appointments. I use a self-driving car to drive me around. Right? Whether we trust the machine learning to do this for us depends on the security issues, whether or not it will have a problem. So this becomes important when we want to use it more often. Okay, so there's still many challenges and many opportunities for applying machine learning in our daily lives, and I hope that we give you some idea about how it worked and also the challenges. And challenges just means that there's opportunities for people to work on this problem and also to use it. So I think that's all I have. And if you have any questions, we are happy to answer them. Any questions? When did I learn how to do machine learning? Yeah, so I only learned in graduate school, which is, I don't want to say the date because I don't know how old I am. Okay, but nowadays, I think this can be pushed back much earlier. Right? Now we have like kids who are doing coding with Scratch, this kind of visual programming. right? And that really seeds the way for other programming. So like for secondary students to do something machine learning, I wouldn't be surprised if they do that. Because a lot of the concepts, and the core concept is very simple, right? Based on algebra and calculus. To use deep learning, you don't actually need to know that, but you just need to know how to run the toolbox and the idea about why it's working, and then try to design it yourself. So people, I think, if you want to do it, you can definitely try to do it.
First, thank you for your very informative and useful presentation. I have two simple questions. First, because most our attendants are students, I want to ask how do you, what do you want to advise to the students? What sort of training they need to prepare for become AI or data scientists? And second question is, how do you position Hong Kong's learning environment compared to other countries like US, China, European, something like that? Thank you.
The first question about how to prepare. So like I said, you can see from the slides that machine learning, it's based on this idea of formulating learning as a mathematical problem. Okay, so in order to use it, it's just a toolbox on the computer. It's like you click and run some data through it. But so to do that, you just need programming skills. Right? But if you want to be a creator, right, or engineer, then you need to know the math behind how it works in order to create new algorithms or create new ways of learning. So I think it depending on where you want to be, right? So having strong math skills and having programming skills would be helpful. And the second question about the learning environment, for university or for secondaries?
Universities or any job opportunities in Hong Kong compared to other countries?
Yeah, I think so at least in our university, I think the education that we provide for data science and machine learning is actually quite good compared to undergraduate in other universities in other places. In Hong Kong, there's also some other data science undergrad programs. But I think, like I said, it's like this curve is being pushed higher, right? Because people are programming earlier, because they have technological skills earlier, then they can do more advanced things earlier. Right? When I learned to program, I was not in primary school. Right? I was in high school, and this is like a side project that I did. Right? Now we have actual camps and schools and things. So I really think that it's good for people to have this, and I think Hong Kong is actually positioned quite well because we have a lot of STEM classes, and the university education from CityU, UST, CHK, they're all quite good. Yeah. They're comparable to other universities. Any other questions?
Question. I think in terms of learning, you have two aspects. One is the coding aspect, and the other one is the data, the big data. So for the data side, I mean, as you said, I think data is key. But where can from a society or from a country's point of view, where can one get the data, and how does it actually efficiently utilize it?
So, can I rephrase your question? Like, how does which part you want to?
For a country that actually has sufficient data.
Yes.
Will be the one which will be leading the development of artificial learning.
Yes. I strongly believe that. That's one of the. I believe that because once you have the data, many of the algorithms they can apply on some. Well, put this way, sometimes the value of the data will not be unleashed unless you have a huge amount of data there. So it's like the deep learning example. Because we already have the data, But because now we have the large amount of data, then we can do the image recognition tasks even better than human. So this is one of the aspects. But also, as Antoni just suggests, not in every application domain will we have that well-labeled huge amount of data, because we want to train the machine, we need to tell them the well-labeled data. And an image is already done, right? But any other task, for example, in finance, we don't have that kind of effort or initiative yet, I guess. But if we already have the data, we just need to spend the human power to do the well-labeled data, and then we feed into machine learning algorithms, perhaps we'll see some change. Yes, that's my take.
And may I take this opportunity to thank once again for Cong and Antoni for their invaluable sharings. Finally, we would like to thank you all for coming here this afternoon. Before you leave, please complete and return the feedback form to our staff at the service counter at the entrance. Thank you.